In the previous video, we talked about evaluation metrics. In this video, I'd like to switch tracks a bit and touch on another important aspect of machine learning system design which will often come up, which is the issue of how much data to train on. Now, in some earlier videos, I had cautioned against blindly going out and just spending lots of time collecting lots of data, because it's only sometimes that would actually help. But it turns out that under certain conditions, and I'll say in this video what those conditions are, getting a lot of data and training on a certain type of learning algorithm can be a very effective way to get a learning algorithm to give very good performance. And this arises often enough that if those conditions hold true for your problem, and if you're able to get a lot of data, this could be a very good way to get a very high performance learning algorithm. So in this video, let's talk more about that. Let me start with a story. Many years ago, two researchers that I know, Michel Banco and Eric Breau, ran the following fascinating study. They were interested in studying the effect of using different learning algorithms versus trying them out on different training set sizes. They were considering the problem of classifying between confusable words. So for example, in the sentence, for breakfast I ate, should it be T-O, T-W-O, or T-O-O? Well, for this example, for breakfast I ate T-W-O, 2 eggs. So this is one example of a set of confusable words, and that's a different set. And so they took machine learning problems like these, sort of supervised learning problems, to try to categorize what is the appropriate word to go into a certain position in an English sentence. They took a few different learning algorithms which were, sort of considered state-of-the-art back in the day when they ran this study in 2001. So they took a variant, roughly a variant on logistic regression called the perceptron. They also took some of their algorithms that were state-of-the-art back then but are somewhat less used now. So the Winnow algorithm, also very similar to logistic regression but different in some ways, much used, somewhat less, used not too much right now. Took what's called a memory-based learning algorithm, again used somewhat less now. I'll talk a little bit about that later. And they used the naive-based algorithm, which is something that I'll actually talk about in this course. The exact algorithms of these details aren't important. Think of this as just picking 4 different classification algorithms, and really the exact algorithms aren't important. But what they did was they varied the training set size and tried out these learning algorithms on a range of training set sizes, and that's the result they got. And the trends are very clear, right? First, most of these algorithms give remarkably similar performance. And second, as the training set size increases, on the horizontal axis is the training set size in millions. As you go from 100,000 up to 1,000 million, that is a billion training examples, the performance of the algorithms all pretty much monotonically increase. And in fact, if you pick any algorithm, maybe pick a quote inferior algorithm, but if you give that quote inferior algorithm more data, then from these examples, it looks like it will most likely beat even a quote superior algorithm. So since this original study, which is very influential, there's been a range of many different studies showing similar results that show that many different learning algorithms can sometimes, depending on the details, can give pretty similar ranges of performance. But what can really drive performance is if you can give the algorithm a ton of training data. And this is, results like these has led to a saying in machine learning that often in machine learning is not who has the best algorithm that wins, is who has the most data. So when is this true and when is this not true? Because if we have a learning algorithm for which this is true, then getting a lot of data is often maybe the best way to ensure that we have an algorithm with very high performance, rather than debating, worrying about exactly which of these algorithms to use. Let's try to lay out a set of assumptions under which having a massive training set we think will be able to help. Let's assume that in our machine learning problem, the features X have sufficient information with which we can use to predict Y accurately. For example, if we take the confusable words problem that we had on the previous slide, let's say that the features X capture what are the surrounding words around the blank that we're trying to fill in. So the features capture that we have a sentence: for breakfast I ate blank eggs. then that's pretty much enough information to tell me that the word I want in the middle is TWO, and that is not the word TO, and is not the word TOO. So the features capture, what are these surrounding words, then that gives me enough information to pretty unambiguously decide what is the label Y, or in other words, what is the word that I should be using to fill in that blank out of this set of 3 confusable words. So that's an example of where the features X have sufficient information to predict Y. For a counterexample, consider the problem of predicting the price of a house from only the size of the house and from no other features. So if you imagine I tell you that a house is, 500 square feet, but I don't give you any other features. I don't tell you if the house is in an expensive part of the city, or if I don't tell you if the house, the number of rooms in the house, or how nicely furnished the house is, or whether the house is new or old. If I don't tell you anything other than that this is a 500 square foot house, well, there are so many other factors that will affect the price of a house other than just the size of the house, that if all you know is the size, it's actually very difficult to predict the price accurately. So that would be a counterexample to this assumption that the features have sufficient information to predict the price to the desired level of accuracy. The way I think about testing this assumption, one way I often think about it is I'll often ask myself, given the input features X, or given the features, given the same information available to a learning algorithm, if we were to go to a human expert in this domain, can a human expert accurately, or can a human expert confidently predict the value of Y? For this first example, if we go to, an expert human English speaker, like you go to someone that speaks English well, right? Then a human expert in English, just really most people like you and me, would probably be able to predict what word should go in here. So a good English speaker can predict this well, and so this gives me confidence that X allows us to predict Y accurately. But in contrast, if we go to an expert in human prices, like maybe an expert realtor, right, someone who sells houses for a living, if I just tell them the size of a house and I tell them what the price is, well, even an expert in pricing or selling houses wouldn't be able to tell me. And so there's a sign that for the housing price example, knowing only the size doesn't give me enough information to predict the price of the house. So let's say this assumption holds. Let's see then when having a lot of data could help. Suppose the features have enough information to predict the value of Y, and let's suppose we use a learning algorithm with a large number of parameters. So maybe logistic regression or linear regression with a large number of features, or one thing that I sometimes do, one thing that I often do actually, is use a neural network with many hidden units. That would be another learning algorithm with a lot of parameters. So these are all powerful learning algorithms with a lot of parameters that can fit very complex functions. So I'm going to call these, we're going to think of these as low bias algorithms, because they can fit very complex functions. And because we have a very powerful learning algorithm that can fit very complex functions, chances are, if we run these algorithms on a data set, it will be able to fit the training set well, and so hopefully the training error will be small. Now let's say we use a massive training set. In that case, if we have a huge training set, then hopefully, even though we have a lot of parameters, but if the training set is sort of even much larger than the number of parameters, then hopefully these algorithms will be unlikely to overfit, right? Because we have such a massive training set. And by unlikely to overfit, what that means is that the training error will hopefully be close to the test error. Finally, putting these two together, if the training set error is small and the test set error is close to the training error, what these two together imply is that hopefully the test set error will also be small. Another way to think about this is that in order to have high performance learning algorithm, we want it not to have high bias and not to have high variance. So the bias problem we're going to address by making sure we have a learning algorithm with many parameters, and so that gives us our low bias algorithm. And By using a very large training set, this ensures that we don't have a variance problem either. So hopefully our algorithm will have low variance. And so it's by putting these two together that we end up with a low bias and a low variance learning algorithm. And this allows us to do well on the test set. And fundamentally, it is the key ingredients of assuming that the features have enough information and we have a rich class of functions. That's what guarantees low bias. And then it's having a massive training set that's what guarantees low variance. So this gives us a set of conditions, or hopefully some understanding of what's the sort of problem where if you have a lot of data and you train a learning algorithm with a lot of parameters, that might be a good way to give a high performance learning algorithm. And really, I think the key tests that I often ask myself are, first, can a human expert look at the features X and confidently predict the value of Y? Because that's sort of a certification that Y can indeed be predicted accurately from the features X. And second, can we actually get a large training set and train a learning algorithm with a lot of parameters in that training set? And if you can do both, then that will often give you a very high performance learning algorithm.